Hello, let me show you the mechanism for this electrophilic aromatic substitution. This is, again, an EAS. And the first step, or the first couple of steps in the mechanism, is to create the electrophile. Let me write that down. Part 1. To create the electrophile, we'll take tert-butanol and protonate it with sulfuric acid. Let's make OH a good leaving group by converting it into water. We did create the conjugate base of sulfuric acid. And water leaves just like this, pops off. Normally that wouldn't happen, but we form a very stable carbocation. We all know this as a tertiary carbocation. And this is our electrophile. It is the species that's going to be attacked by the nucleophile. The nucleophile in your reaction is the 1,4-dimethoxybenzene. We also kicked out water. Okay, next step. Next step is going to be the attack. Let's take our 1,4-dimethoxybenzene. I'm going to draw the double bond here, like this. We have our electrophile, very attractive, right, to the nucleophile. We do break this double bond, and we call this breaking the aromaticity, because we no longer have benzene. What we do have, though, is, let me show you. So where can this tert-butyl group go? It goes down here. We have an H, and we have our tert-butyl group. Okay. We do have a carbon that's naked. This carbon up here doesn't have 4 bonds, so it's positive. We call this the arenium ion. It came from the aromatic benzene. A lot of times you'll hear the ring described as aromatic, but also as an arene. Arene. But when we attack an electrophile, we get the ion, and this is called the arenium ion. We have still water in the mixture. And what happens here is we reform aromaticity. It's a little bit confusing, but in this step, we are reforming aromaticity. Reform. If you haven't gotten to aromaticity yet in lecture, this will all make a lot more sense once you get to it. But basically, we are reforming the benzene part of the molecule. And that is done by this water grabbing this hydrogen and reforming that double bond. And that's how we get one of the tert-butyl groups onto the ring. Now, the position of this tert butyl group, it actually doesn't matter. The first one, it doesn't matter because if I had put it here, it's still the same product. If I put it here, still the same product. But we are doing a dialkylation. So by the way, the other thing that I want to mention here is that alkyl groups are electron donating. And let me put that in light blue. Alkyl groups are electron donating groups. You know, this methoxy group right here, that's also electron donating. And that activates the ring. Electron donating groups activate or make it more reactive. Activate the ring. So when we put in another electron donating group down here, we make it even more reactive. So this is even more activated. And that's why we're going to get a second alkylation. And the position of that second alkylation can occur in a couple places. It wouldn't occur here because one of the general rules is you don't add a group in between two existing groups. So that's not good. We could put it here, but more likely it's going to go here. And I won't go through why. That will come in lecture. But we do have to add a second tert butyl group. Okay. You know why this is called a tert butyl? It has 4 carbons arranged in this letter Y configuration. Okay. The challenge is, how do I get it to go to this carbon here? We can't put it here, too crowded. You don't put it in between two groups. How do we get it here? Well, we got to use this double bond. Okay. And so we're practicing more. This is our second addition, or really it's a substitution. And we got rid of this double bond on the upper left. Okay, so what did we add? We added the tert butyl group here. And do you know where the double bond, do you know where the carbocation is right now? It was this carbon here that's naked. Okay. The next thing to decide is which hydrogen to remove. Okay, are we going to remove the hydrogen that's on this carbon here, or are we going to remove the hydrogen that's on this carbon? Well, look at the final product, right? The final product, this hydrogen is still there. It was this hydrogen. So it's normally, it's not normally, it's always the hydrogen that on the same carbon as the group that was added, right? This hydrogen right here. So it makes sense, right? See how there's no hydrogen here? Same thing in this case. Let's draw the hydrogen we're going to remove. That one. And let's remove it. And what are we doing again? We are reforming aromaticity. And our final product. It's a short mechanism, but you're doing this alkylation twice. And it's going to go in these two positions. Okay, is that our final product? Yes. And we did create some acid. That's good because we could start the process again by protonating this alcohol with this acid as well. It doesn't matter which acid you use. Okay, let's zoom out. Very short mechanism, or relatively short mechanism. And again, this is called an electrophilic aromatic substitution. Specifically, it's a alkylation of a benzene derivative.